Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Abdulrahman Ragi. Today I will be talking about wave polarization, which is a topic in our course Electromagnetic Waves and Applications, in which I am taking with my instructor, Dr. Hussein Atiyah. So first, what is wave polarization? Imagine we have an electric field with X and Y components. Let's call the magnitude for X to be A1 and the magnitude for Y to be A2. Now, the direction of this electric field will be here with a certain phase, and the total magnitude will be the square root of A1 square plus A2 square. And this phase is nothing but the arctan or tan inverse of A2 over A1. Now, this behavior of the electric field is at one certain point of time. Now, what happens if we are imagining a wave that is propagating, let's say, in the Z direction? This is being the X component, and this is being the Y component. Now, we are at some point here, let's say, and this is the behavior and the direction of our electric field at this certain point. Now, what happens if we check this certain point at different times? The behavior of electric field will differ. It could be going in this direction, it could be going in this direction, it could be going in the opposite direction of the first one. Now, tracing this behavior through time is the polarization. Now, we have three types of wave polarization. The first one is linear, in which the polarization will be nothing, the trace of the electric field behavior will be nothing but a line. And this can happen if we have a phase difference of 0 or plus or minus 180 degrees. For radian, we can say plus or minus n pi. So the wave polarization will be a line. For our previous case, it will be like this in one certain point of time and like this on other. It could be a line in any direction, like this, like that. This is for the linear polarization. Now, for the circular polarization, there has to be two conditions that need to be fulfilled. The first one is the magnitudes must be equal. A1 must equal A2, and the phase difference must be equal to plus or negative 90 degrees. Or for radian, we can say odd integer multiples of pi over 2. This is for the circular. For the linear, they can have any magnitude, but the phase difference must equal 0 or plus minus 180 degrees. Now, for the elliptical polarization, we have two cases. The first case is when we have a different magnitudes. Here, the phase difference must not be equal to 0 degrees or plus or minus 180 degrees, or in radian, it is plus or minus n pi. The phase difference should not equal these values. Once we have any of these values, it will not be an elliptical polarization, it will be a linear polarization. The other case is when we have the magnitudes of them to be equal. A1 equal the magnitude of A2. Here, the phase difference should not be equal to 0 degrees or 180 degrees, negative or positive, as well as it should not be equal to 90 degrees. From here, you can tell that the elliptical is nothing but if the conditions for the circular and the linear do not happen. So we can say that the elliptical is the general case. If one of the circular and linear polarization conditions apply, then it will no longer be an elliptical polarization. Now, how do we determine the direction of the circular or elliptical polarization? For the linear, it will be a line, so there will be no sense of direction, just going in a line. However, for the circular and elliptical, imagine this is at one certain point of time, this is at a second point of time, this is at a third point of time. Now, how do we determine the direction of the polarization? Is it right-handed direction or left-handed direction? Now, imagine the propagation direction, which is in the z direction, is out of the screen towards you. Now point your right thumb towards yourself and curve your four fingers, these ones, to the left in this direction. Now, if the polarization is going through the same direction as your curved fingers, we call this the right-handed polarization. However, if you are still pointing your thumb towards yourself and your fingers are going to this direction as well, but the polarization is going to the opposite direction of your curved fingers, then this is not a right-handed polarization. This is a left-handed. Now, get your left hand and point your left thumb towards yourself and curve your fingers, and you will be able to match the direction of the polarization. Now, is there another way that we can find the right hand or left hand direction? Yes. Now, let's talk about the phase difference. The phase difference is nothing but the phase of y minus the phase of x. We'll do another one here to differentiate them from each other. Okay, now if we have the phase x leading y, meaning that the resultant phase difference is negative, which means that x is bigger than y, we have a right-handed polarization, whether it is circular or elliptical. However, if we have a y, the phase of y leading the phase of x, meaning that y is bigger, which means that the resultant phase difference is positive, here we will have a left-handed polarization, whether circular or elliptical. Now I will verify these things that I have said with two very nice websites from our book. Now, stay with me on the right website. Here you can see a linear polarization. If we trace the polarization, it will be a line. But let's leave that for later. Now let's make a circle. We said that the circular polarization must have a equal magnitude for both components of the electric field, and the phase difference should be multiple odd integer multiples of 90, whether positive or negative. So let's see the trace, which is very clearly a circle. Now this polarization, of course, the propagation direction is towards you, is out of the screen. So if we apply the right hand polarization, so point your right thumb towards yourself and curve your fingers, you will find out that you are moving in the opposite direction of the polarization. So it's not a right hand. If you use your left thumb, you will find out that your fingers are curving with the polarization direction. Now, to verify what I have said in the last slide, we have the phase of the y component is 90 and the phase of the x component is 0. So y is leading x by 90 degrees and the phase difference is positive. And if you check the left hand or right hand, it will be a right hand polarization for this circle. It can be the same case for an for an ellipse. Let's see, this is an ellipse. And the direction of the polarization is left-handed as well. Now, let's review what I have said about polarization. What is polarization? Let's check the left-sided website. If we start this at equal magnitudes and 0 phase difference, this is a line polarization or linear polarization, and you can see that from the squares on the left and the right. So I will be moving this square. So the polarization is nothing but the trace of the electric field behavior at one spot when the wave is passing or propagating. So if we move this square at the same pace as the wave, you cannot tell what is the polarization or what is the behavior of the electric field. You must choose one spot on the propagation direction and see the behavior of the electric field through time at that one spot. Let me repeat that again. I will try to move at the same pace as the wave. You can see that we cannot tell a difference from each point if we are moving at the same speed. So the polarization, as I said, is at one spot in the propagation direction. You will check the behavior of the electric field and trace that behavior. That will be the polarization. Now, let's review the types of polarization that I have talked about. We said that the linear on the right website here, the linear is when we have a phase of the phase difference of 0 degrees. You can see that this is a line, or it can be negative or positive 180 degrees as well. This is also a linear polarization with a line on a different side. So for the elliptical, it will be it could be a phase difference of 90, but the magnitudes will be different. If the magnitudes are the same, then this is a circular polarization. Let's change the magnitude of x, make it almost half. Here we have an ellipse. If y is bigger than x, the magnitude of y is bigger than the magnitude of x, we will have the major axis of the ellipse at the y direction. However, if y is smaller than x, we will have the major axis at the x direction. This is for the 2D representation of the polarization when you are looking at it from the propagation direction. Let's check the left website to verify what I have said. Also, the polarization can only be affected by three things: the magnitude of the first component, the magnitude of the second component, and the phase difference. Nothing else will affect the polarization. And I will show that here right now. This is the case for the linear, as I said. This is a linear polarization. Now, what if I change the frequency? We have the frequency here is 1 to the power times 10 to the power 9. Let's make it very small. Let's update this. And there's no difference at all. Let's make it to the power 9 and show you again. There is no difference at all. So the frequency is not affecting our polarization. Let's check the permittivity, the relative permittivity. Let's make it very big to make a very big difference if there is any. So let's check. There is basically no difference at all. The polarization is not affected by the permittivity. So let's reset the permittivity to 1. And let's check the permeability. Let's make it very big. Let's update our values. And let's check the phase planes. And it's still a linear polarization. Let's check the case if we have a circle. This is our circle polarization. Now let's reset the permeability. Let's update the values and see if our circular polarization is affected. It is exactly the same. Now let's check this is nothing but the reference amplitude, which is the amplitude of x scaled by the factor scale here, and the same. So it's basically E0 multiplied by the scaling factor of x and scaling factor of y. We can change the scaling factor with this. So to show you a better look of the polarization here, let me increase the length displayed to 10. I forgot to update this. Let me update. And we change the length displayed to 10. And you can see that the trace of the behavior of the electric field at one point of time is a line. So let's stop here. It is a line. Of course, while it's moving, it will be like this angle here. But let's see the circular polarization. Now the wave is propagating towards the Z direction, and we can see that the behavior of the electric field is going in a circular motion. Now, while the wave is moving, it looks like a spring, but if you are looking at it from one certain point of time, or one certain spot, not point of time, one certain spot for different times, you will see that it is a circle. This is you can choose any spot you want. And depending on the phase, it will be an ellipse, a circle, or a line, either positive, negative, or anything else. Now, I hope you are familiar with what is wave polarization, the types of it, how to determine in what direction the polarization is, either visually or with the phase difference formula. And that's it for me. Thank you for watching.